Hello. So today we are starting our Sequences and Series chapter, chapter 7, and this first lesson is about how we use the new notation to write sequences and then writing a rule for the nth term of a sequence. Also, we're going to be writing rules for series using summation notation, which again is new, and then how to find the sum of a series. So down here we've got some information that a sequence is an ordered list of numbers. So basically a sequence is an ordered list. A finite sequence is a function that has limited number of terms. So finite basically has an end and is limited. So when you have a finite sequence, the domain, which is your x values, are the set of basically your counting numbers or natural numbers that start with 1, 2, 3 on up to a specific number n. The values of the range, or your y values, are called the terms of the sequence. So if we think of this as a table of values, your domain, which is your x values, and your range, which are your y values, would look kind of like this, where the relative position of each term. So the first term in the sequence we call a sub 1. The second term in the sequence we call a sub 2, third, and so on, all the way up to the nth term. So the nth term is called a sub n. So these are the actual terms that are in the sequence, but the 1, 2, 3, 4 on up to n represent where they are in the sequence, whether it's the first, second, third, fourth, or the last term, which we call the nth term. All right, well, there's another word here, infinite. Infinite sequence. So if you have an infinite sequence, basically it means it has no end. It goes on forever and ever. So has no end or limit. So it does not end and there is no limit. We'll get to series in a minute when we get to the next example. But for right now, an infinite sequence is a function that continues without stopping, and the domain, or x values again, is the set of positive integers. So integers hold. Okay, so I guess my recording time is limited, so I'm gonna just pick up where I left off. So here we've got a couple examples of a finite sequence and an infinite sequence. Notice the markings at the end. When it's an infinite series or sequence, it's going to have those dot, dot, dots at the end. So that's really important if you're showing that it's an infinite sequence. So it doesn't end. But here we don't see the dot, dot, dot at the end. So it has an end. So that's important when you are discussing the difference between finite and infinite. So a sequence can be specified by an equation or a rule. So equation or rule. So in this finite sequence and in this infinite sequence, you can see they're basically the same numbers, but this one goes on forever and ever. Well, there's two ways that we could write the rule. We can write the rule as a sub n, which is sequence notation, where the n represents the number, the place value, so like the first term, second term, third term, fourth term, and it's also representing the number that you're plugging in for n. So if n is 1, you're going to get 2. If n is 2, you're going to get 4. If n is 3, you're going to get 6, and so on. So this is one way of writing the rule or the function. This is another way, and that's function notation. So whether you see it looking like this or looking like this, you should be able to figure out the first and in these examples here, you have to find the first 6 terms, or if I asked you to find the first 5 terms or 10 terms, you can use the rule and just plug in the numbers 1 through whatever, in this case 6, to find the terms of the sequence. So in my first example here, example 1a, they give you this rule. So the easiest way I like to do it is to make a table of input and output values. So the n is my input value, and the a sub n is my output value. And the rule for a sub n is right here. I'm going to take 1/2 of the number that I'm plugging in for n minus 3. So we have to do this for the first 6 terms, which means we're going to find the first term, the second term, the third term, the fourth term, the fifth term, and the 6th term. So we've got to find the first 6 terms. So if I take 1/2 of 1 minus 3, half of 1 is a half, minus 3 would be negative 2.5. If I take 1/2 of 2, which is 1, minus 3, I'm going to get negative 2. If I take 1/2 of 3, which would be 1.5, minus 3, that's going to equal a negative 1.5. If I take 1/2 of 4 minus 3, so half of 4 is 2, minus 3 is negative 1. If I take 1/2 of 5, that's 2.5, minus 3 will give me negative 1/2. And then last but not least, 1/2 of 6 is 3, minus 3 is going to give me 0. So when you're writing your answer, make sure that you write it as a list. So if you're asked to write the first 6 terms, so if you're writing the first 6 terms of a sequence, these are the numbers that we are writing, and we're writing them in a list. So your answer should be a list and look like this: negative 2.5, comma, negative 2, comma, negative 1.5, comma, negative 1, comma, negative 1/2, and 0. So that is the answer to this example. All right, the other example is very similar, except the notation is a little bit different. Instead of saying a sub n, they're saying f of n, which basically is the same type of process, where your n is going to be your input value. The rule is going to give you the output value, and you're going to plug in again finding the first 6 terms, so you're going to be plugging in 1 through 6. So again, I like to make a table to show my input and my output values. This time my input still is n, but my output is called f of n, which is like function notation, and that's going to equal the negative 2 to the n minus 1 power. So now I'm going to set up 1, 2, 3, 4, 5, and 6. And then I'm going to apply the rule, negative 2 to the 1 minus 1 power. Well, 1 minus 1 is going to be 0. Negative 2 to the 0 power equals 1, because anything to the 0 power is 1. And then we've got negative 2 to the 2 minus 1 power. So this number right here that we're subtracting 1 from is what our n is. So we're taking 1 minus 1, 2 minus 1. The next one's going to be 3 minus 1, 4 minus 1, and so on. So do the math. The negative 2, now 2 minus 1 is the first power. Anything to the first power? All right, so continuing where I left off, we plugged in the 1 and 2, but now we're going to plug in the 3. Negative 2 to the 3 minus 1 power equals negative 2 to the second power, which equals a positive 4. And then we have negative 2 to the 4 minus 1 power, which is going to be negative 2 to the third power, which is a negative 8. Negative 2 to the 5 minus first power is going to equal negative 2 to the fourth power, which equals a positive 16. And then the last one, negative 2 to the 6 minus 1 power equals negative 2 to the fifth power, which then is going to equal negative 32. So if I'm writing my list now as my answer, the first number in my list was 1, so it's these numbers right here that I got after. Those are my output values. So the first number in the sequence is 1, the second term is -2, the third term is 4, the fourth term is -8, the fifth term is 16, and the sixth term is -32. So there's my first 6 terms of the sequence. Notice also that the signs are alternating between positive and negative and positive and negative. The reason that happens is because our base is -2. So we're going to be getting a positive number every time there's an even power and a negative number every time there's an odd power. That's going to be important when it comes to time to writing the rules if you're given the sequence. And actually that's what we're doing next. So on the next page here we've got series and summation notation. Let's see. Okay, so I guess we're writing it with series or summation. Okay, but so we will be writing these rules, but I guess we're writing them with summation notation. But see how here we have a negative, positive, negative, positive? That's what I'm talking about. So when we write the rule for this series, we are going to have a negative number that's being taken to a power to make it go negative, positive, negative, positive, so that the results are alternating. All right, so we'll get back to that. Let's now go back to the top of this here. I have series. So series was one of those terms that we're supposed to define on the front side, one of our vocabulary words. And basically a series is when the terms of a sequence are added together. So it's basically the sum of a sequence. So let's go back to the front page and we're going to complete our vocabulary here. So the series is, or if you're asked to find a series, you're asked to find the sum of a particular sequence. So you're finding the sum of the sequence. Okay, so how do we do that? Well, in the example on the other page, when we were given a finite sequence rather than a series, it was just a list of numbers. It was 2, 4, 6, 8. But so let me show you. So the sequence on the last page was 2, 4, 6, 8. So the difference between writing a sequence and writing a series is basically you're adding them up. And the infinite sequence, again, had commas in between, 2, 4, 6, 8, dot, dot, dot. So the dot, 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 again, signifies that it's infinite. But if you're writing a sequence, you're just putting commas in between, where if you're writing a series, you're going to be adding. All right, continuing on. All right, so the next part here says you can use summation notation to write a series. So for example, we have these 2 series that we were talking about, or that I showed you up here. Okay. So summation notation is kind of a new word, so maybe we should highlight that. So summation notation is this stuff right here. This is the way it looks. So you can use summation notation to write a series. The 2 series right here are listed here in summation notation. I want to point out some of the features of it. So so this 2 plus 4 plus 6 plus 8 is the same as this thing here. But notice that in the summation notation, you've got this symbol called a sigma. It's a capital Greek letter. But notice that this is basically the first number in the sequence, the second number in the sequence, the third number in the sequence, and the fourth number in the sequence added together. So this little I, there's a tiny I there on the bottom. That I is what we call index. So down here, the index of the summation is I. And I just represents what order or what number in the sequence it is. So the first number in the sequence is 2. So we're going from 1 to 4. So the lower limit, and that's something else we're going to talk about, the lower limit for the index is 1 and the upper limit is 4. So we're going to be substituting 1 through 4 into this rule, and I is not and it's not the same as imaginary number. So we're using the variable I, but this time it's not representing imaginary number, it's representing the index of your summation. So when we add these up, 2 plus 4 plus 6 plus 8, you're going to get a sum of 20. So that's how you would figure out the sum. So this is the notation that you're going to see, but you basically find the first term through the fourth term and you add them up and you get 20. Now if it's an infinite series, you obviously cannot keep adding forever and ever. So, but the way that you would write the notation would be like this. The first number in the sequence, or the first term in the sequence, again, your I. So this is your I, your index. So you got your first number in the sequence, the second number in the sequence, the third, the fourth, but it's going to keep on going up forever and ever into infinity. So we still have the same rule, 2I, but it's the index that's changed. So it's from 1 to infinity now instead of 1 through 4. So this is, again, your finite series means that it's going to have a number up here. An infinite series would have an infinity sign at the top. All right, so for both series, the index of the summation is called I. The lower limit is, the limit of the summation is 1. So again, that's the lower limit. And then this thing up here at the top is called the upper limit. A lot of new words, but it's all written in here in the definitions. All right, so let's see what else is important here. Okay, so sigma, we talked about the Greek letter sigma, that's the symbol that's used. Oh, so besides calling it summation notation, so some people will call it summation notation, or some textbooks will call it summation notation, but you'll also hear it called sigma notation. So sigma notation basically equals summation notation. They're the same thing, it's just a different way of saying it. Just a different word. Summation notation, sigma notation, same thing. All right, so here we go. We're writing our series. The next thing we need to do, write the series. Okay, so in order to write the series, the first step is, so step 1, write the rule. So we need to figure out, how are these numbers, where are we getting these numbers from? So a good way I like to do this again is, let's say that's my I, or my index. The first number in my sequence is 1, or the first number of my series is 1, or 5. The second number in my series is 10. The third number in my series is 15, all the way up to the nth number, which we would figure out what this number is. So let's just look at these three. What could we do to 1, 2, and 3 to get 5, 10, and 15? Well, hopefully you can realize that you're multiplying by 5. So my rule is basically take 5 times my index. So then, looking at the last term here, since it does end, this is a finite series because it ends, where this one would be an infinite series because of the dot, dot, dot. So that dot, dot, dot shows you that it goes on forever and ever. So this one actually has a final number. This one does not. This one does have a final number. So this one again will be finite. So we have to figure out now, since when it is a finite series, we want to figure out, well, what would the index be if the output is 100? Well, if we figure out our rule is 5 times the index, or 5 times what, then would equal 100? 20. So 20 is then our upper limit, and the 1 then is going to be our lower limit. So now we have all the information we need, we can write our series in summation notation. So leave a little bit of space above and below your sigma. So there's my sigma, and I equals 1 is going to be my lower limit, 20 is my upper limit, and the rule is 5i. And that's it. So that's how I would write the series using summation notation. So this is my answer. All right, so let's try another one. Let's see if we can figure out this one. Again, you want to figure out what is the rule, what's happening. So if the first number in the series is 6, and the second number is 36, the third number is 216, the fourth number is 1296, these numbers are getting really big really fast. So we've done a lot of things with exponential, so hopefully you're recognizing that if you take 6 to the first power, it equals 6. If you take 6 to the second power, it equals 36. If you take 6 to the third power, it equals 216. If you take 6 to the fourth power, you're going to get 1296. So that's basically our rule. The rule is that you're going to take 6 to the power of I. But you know what? Instead of I this time, I'm going to use n. So you don't have to always use I. You can also use n. So basically 6 to whatever the nth power is. So if n is 1, 2, 3, 4 on up into infinity. But if you're going to use n here, then you're going to have to use n in the summation notation also. So your variable here has to match. Whatever your variable is here has to match there. So if I decide to use n, then I have to make sure that I have an n here to match my rule. Again, my lower index is 1, and my upper index, since it's continuing forever and ever, there is no end, it's going to be infinity. And then my rule, 6 to the n power. And again, make sure your variable matches both places. And that's my summation notation. All right, the C problem has a little bit of a twist in it. It has alternating signs from negative to positive. So that indicates that we're going to have to be taking a negative number to a power. The first number in our series is -2, the second is 4, the third is -8, the fourth is 6 positive 16, and the fifth is -32. So we now have to figure out, well, what could we do to get an output of -2, +4, -8, +16? What is the pattern here that we're seeing? Well, 2 to the first power is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32. But because it's alternating signs, your rule is going to have a negative number inside. So the -2 to the first power would give us the -2. -2 squared. Okay, so instead of n1 here, I can't put 1. I got to put my variable there. So -2 to the nth power. So -2 to the first is -2. -2 to the second, +4. -2 to the third, -8, and so on. So that's my rule. All right, so my upper limit now, that's another piece of information we need because it's finite or it ends. You are going to have a number for your upper limit. It's not just going to be infinity. So 5 is our upper limit. So here we go. Let's write our rule or our summation notation. That's what it's called, summation notation. I'm using n again, so n equals 1. but my upper limit, the last number that I'm going to plug in for n, is 5, and my rule -2 to the nth power. So again, watch that your variables match in your summation notation. All right, moving on. Example 5. The next thing that you're going to be doing is finding the sum of a series. So what's unique here is now they're giving you the summation notation. They're telling you what your lower limit is, what your upper limit is, and this is basically your rule. So let me write this a little bit bigger so we can point out the different pieces of this thing. So the 2 is my lower limit. And some of you are thinking, I thought, you know, all the lower limits had to be 1. Well, in a lot of these, yes, everything that we've done so far, the lower limit has been 1, but it doesn't always have to be 1. So you could have a lower limit of 2. So be careful of that when you're doing problems in your homework or on a quiz or a test. If that's a 2, then you have to start with 2. You're not going to start with 1. And then this is your upper limit. And then this thing here in parentheses is your rule. So just like I did on the last page when I was trying to find the first 6 terms of a sequence, I'm going to make a table. So let's make it horizontal here to make the most of my space. So I have my input and my output, which my input is n and my output is basically my rule, n over n minus 1. So here we go. We're going to have to, oops, I put 1. My lower limit is 2, not 1. So again, I made that mistake I just told you to watch out for. So if I substitute 2 now into this rule, I would have 2 over 2 minus 1, which is 1, which would just equal 2. So 2 is the simplified answer, output. If I substitute 3 in the numerator is just 3. 3 minus 1 would be 2. And 3 halves can't be simplified, so I'm just going to leave it as 3 halves. 4 would be the next input. So if I put 4 in for n, I would have 4 in my numerator, and then 4 minus 1 would give me 3 in my denominator. And then the last number I would substitute would be 5. So 5 in the numerator, and then 1, which is 4, in the denominator. So then what I need to do is I need to add up my output values. So there's only 4 numbers because the lower limit was 2 and the upper limit was 5. 2, 3, 4, 5. Your second, third, fourth, and fifth term are only going to give you 4 outputs. So the sum, going back to this notation up here, is 2 plus 3 halves plus 4 thirds plus 5 fourths. And to save time, I'm going to use my calculator that can do fractions. And if I add all that up, I'm going to get 6 and 1/12. And that is my sum. So again, we answered the question, find the sum of each series. So the 6 and 1/12 is the sum of that series. All right, the next one here, a little bit more going on. We've got a square in here, oh no, but our lower limit is 3, our upper limit is 7. So I'm going to make a table here of k. Now k is my input value, and the k squared minus 1 is my output value. Since my lower limit is 3, the first number I'm going to substitute is 3, but then I'm going to substitute 4, 5, 6, and 7. All right, so here we go. So 3 plugged in here, squared would be 9, minus 1 is 8. 4 plugged in for k, 4 squared, 16, minus 1, 15. Plug in your 5, 5 squared is 25, minus 1 is 24. plug in your 6. 6 squared is 36, minus 1 is 35. And last but not least, take your 7 and square it, you get 49, minus 1 is 48. So those are our numbers in our sequence, but then we have to take the sum of them. So we're going to take the 8 and the 15 and the 24 and the 35 and the 48 and add them all together to find our sum, which is 130 when we add that all up. All right, so 2 examples there of finding a sum of a series. So these ones were kind of nice because we only had to plug in 5 different numbers, or we had to plug in this one we only had to plug in 4 numbers. Well, what if we had something that we had to go from 1 to 25 and we had to plug in 25 different numbers? Well, that would take a really long time. A computer would help us with that, which would be great, but there are some series that have special rules or formulas to help us find the sums of the rule, or the sum of the series. So there are 3 special rules or 3 special series that we are going to look at. So finding the sum of special series. So these are special. So the rule here is just 1. Unlike the last one, or last couple, we had a rule that was k squared minus 1, or our rule was n over n minus 1. So the rules were different. Here our rule is just 1. So the output value is going to be 1 for all of our input values. In this second one, our rule is I, which basically is the same. So basically it's saying the output value is going to be the same as the input value. So if I is 1, the output is 1. If I is 2, the output is 2. Well, if you do this with 1 through 32 numbers or something, I think we're going to do down here, 1 through 6, you're going to find that there is a formula to help you find the sum. So there's a special formula that we can use to find the sum of this special series. And then the last one that has a special formula or a special rule or series is when you have to take the index and square it and then add that together. So this is the formula to find the sum when the rule is to take the index and square it. So let me kind of show you, well, I guess these examples here will show you what these rules really mean. So if you didn't quite understand what these rules represent, you'll understand it better when we actually plug in some actual values. So, oh, and going back to this one, the formula to find the sum, oh my goodness, yeah, I can't spell here. Formula to find the sum is just n, which is, again, the n is the same as your upper limit. So whatever number you have here as your upper limit, if your rule is just 1, which means your output for every input value is 1, the answer, or the sum, is the same as your upper limit. It's going to equal your upper limit. So in this example here, A, the rule is basically 1, which basically means you're going to add the first term in the sequence is 1. The second term in the sequence is also 1. The third term in the sequence is 1 again. The fourth term in the sequence is 1. So we're going to keep adding 1 over and over again until we get 34 ones added together. So that's the idea of what you're doing. So for every single number in the sequence, the output is just 1. So if you have 34 numbers in your sequence and you're adding 34 ones together, it's going to equal 34. So that is the sum of 34 ones being added together. So hopefully that rule makes more sense now that you see it's just taking 1 plus 1 plus 1 plus 1 34 times. So that's why the number up here in your upper limit is going to equal the sum of all of those ones. All right, the next one, example B, separate that. All right, so if we were to, this one actually is not so hard to find. We don't necessarily need a rule for this, but if we used the rule, or the formula, sorry, the rule is K, where in this case it was I, here it's K. So we're just switching up the variable, but the formula is going to be the same. So if I use the formula to find the sum, I'm basically going to plug in my upper limit. So the n is my upper limit. So in this case, n equals 6. So I'm going to take 6 and substitute it in for n. Substitute 6 again for n here, plus 1 divided by 2. So I'm just substituting 6 in for n. Now I'm going to simplify this. So the 6 plus 1 gives me 7 times the 6 would equal 42 divided by 2, which gives me 21. So the sum of this series is 21. So that would be my answer. And in the last one, 34 would have been my answer, because that's the sum. Well, let me show you why this is going to be 21. And because we're only going from 1 to 6, it's not going to be hard to show it. So if my K value is 1, my output is also 1, because the output they're basically saying is K. So whatever the input is, the output is going to be the same thing. So the output is also K. If I put 2 in, I'm going to get 2 out. If I put 3 in, I'm going to get 3 out. If I'm going to put 4 in, I get 4 out. If I put 5 in, I get 5 out. 6, I get 6. 7, I get 7. So these are my output values, which are the same as my input values. What the summation notation is telling you to do is add these up. So if I were to add 1 plus 2, I get 3. Plus 3 is 6, plus 4 is 10, plus 5 is 15. This is not, oh, yeah, I accidentally went to 7. I'm only supposed to go at 6. I'm like, something's not adding up. Okay, so going back, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 would be 21. So you would end up getting a sum of 21 if you added the output values together. But if you had to find, let's say your upper limit was 32, the formula is going to be a whole lot easier than trying to add 1 plus 2 plus 3 plus 4 plus 5 all the way up to the 32nd number, or 32. So that's where the formula kind of comes in handy. But again, you can only use the formulas, these 3 formulas, if your rule is just 1, I, or in this case K, or whatever the variable is. So if the input matches the output, or if the input is being squared. So that's our third. So in the third case here, we've got I squared, and we're going from 1 to 18. So I don't know about you, but I'm not going to take 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to 18 squared. I would much rather use a formula that somebody else has already figured out. But the number that I'm going to plug in for n is 18. So you're going to plug that n in here, in there, and in there in your formula. And in the last one, the n was substituted here and there. And the first one, the formula n, is just your sum. So you don't have to substitute it into anything. The upper limit is your sum. All right, so going back to the I squared, our upper limit again is 18. So I'm going to take 18 times 18 plus 1 times 2 times 18 plus 1. And then divide that all by 6. So that's part of the formula. That number at the bottom doesn't change. It's just the n that you're going to replace with whatever your upper limit is. So now we just have to simplify. So in my numerator, I've got 18. 18 plus 1 is 19. 2 times 18 is 36. Plus 1 would be 37. And then I'm going to multiply those together and divide by 6. So again, I'm going to use my calculator to help me do the calculations, and I get 2,109. So that is my sum, or my answer. All right, thank you very much. That is the end of our notes for 7.1.